Hello, my name is Yoo Jung, and I present our paper titled Diversity-Aware Channel Pruning for StyleGAN Compression. First, let me summarize our paper briefly. Our research targets StyleGAN compression, focusing on compressing the generator network. We begin by pruning the original model and to initialize a lightweight version. Then, we fine-tune this model using knowledge distillation and adversarial loss. Our approach refines the initial channel pruning stage by prioritizing sample diversity. Since image differences are closely related to sample diversity, we aim to retain channels that significantly contribute to these differences. Our compressed generative model shows generated samples comparable to the teacher model, utilizing only 30% of the teacher's channels and just 10% of the flops. Let's start with an overview of the StyleGAN architecture. StyleGAN consists of a mapping network and a synthesis network. The mapping network uses multiple fully connected layers, and the synthesis network uses multiple modulated convolution layers. In our paper and this presentation, we call the latent vector as the output of the mapping network, which takes noise Z as input. We focus on the latent vector W, known for its semantic disentanglement and extensive usage in image editing research. The synthesis network occupies over 98% of the total model, so we focus solely on it for lightweighting. Previous work shows that pruning the mapping network degrades the full generator's performance more than pruning the synthesis network. Thus, for compression, we first prune the synthesis network of the teacher model, then we fine-tune the student model by distilling knowledge from the original model and training it with GAN loss. Previous lightweight GAN models often lose information related to sample diversity. Many works measure sample diversity using recall score compared to real data. We observed that previous compressed models struggle with diversity as shown in this figure. To address this, we focus on preserving the distinct semantics of the generated samples. Here, I explain how we collect channel-wise gradients for calculating channel impedance scores. We sample thousands of latent vectors from noise and the mapping network. Then we adopt PCA from GAN space to collect latent directions. Next, we generate two images using the latent vector and the perturbed latent vector. Then we calculate the error and image difference loss and backpropagate it through the synthesis network, repeating this step for 5,000 times. Now let's discuss how we calculate channel impedance scores using these gradients. The common approach averages the gradient of cross channels. However, if a specific latent vector consistently induces high absolute gradient value in a channel, it can interfere with desired channel selection. For example, in this figure, channel I gets high gradient and it is more sensitive to the latent vector than the perturbation, but channel J shows high gradient for specific directions, like D1. So we designed the channel impedance score to retain J rather than I by measuring the variance of gradient over perturbations instead of averaging. Our channel pruning method enhances both the FID and recall scores. We generate images more similar to the teacher model compared to previous compressed models. For our ovulation studies, if we use random directional vectors, we see a slight decrease in performance. This highlights the importance of perturbation in capturing sample diversity, regardless of whether it's random or PCI derived. Also, our diversity-sensitive impedance scores improve generative ability compared to the average-based score for both datasets. In conclusion, we have tackled the challenges of maintaining sample diversity in a compressed StyleGAN generator compared to each teacher model. Our proposed channel pruning method, DCP-GAN, comprises two key components: latent perturbation-induced gradient and diversity-sensitive impedance score. Through extensive experiments, we have shown that our pruning method significantly improves generation performance within the StyleGAN architecture. Thank you for listening.